Okay, hi everyone. So this is the second lecture on the topic of autoencoders. We began autoencoders last week, and it is also the second chapter in the part 2 of our study of deep learning. Part 1 was all about deep learning, current state of the art. And part 2 is about research topics in deep learning. So we're still at the beginning topics. It's about representations. And so we talked about autoencoders last time, what they are, how autoencoders are trained with input output being the same thing, and we find some kind of a representation in between as a representation of the input, and from which we can construct the output as well. What today's lecture is delving a little more deeper into it, that the representation that we learn or the embedding that we learn is lies on a low dimensional manifold. Manifold is like a sheet of paper or some low dimensional object. For example, a sheet of paper in our three-dimensional world is a low dimensional object. It's just a surface. It can be flat, it can be curved, but it's still we call it as a two-dimensional surface. Or if you are in a two-dimensional world, like on a sheet of paper, a curve, a piece of thread would be a line on it, would be a one-dimensional object. So we have manifolds that can be three-dimensional, two-dimensional, one-dimensional, and so on. Zero-dimensional would be a point. So these are the kinds of representations that autoencoders come up with. And we want to discuss what is the nature of this manifold, and why is it necessary to know what kind of manifold is being generated. And because we get a few samples that we're training on, maybe even a large number of samples we're training on, together they define the manifold. Each training sample becomes a point on the manifold or an embedding on the manifold, and all of the training samples together creates that surface. And of course, machine learning is all about generalization, about samples we have not seen. So if we wanted to generate samples from our manifold, we want to make sure that it lies on the manifold rather than off of the manifold. So knowing where we are on the manifold is useful. Another example I can give is, supposing we are medical people, maybe orthopedics people. We have three-dimensional scans of the vertebral column of some patient. So a vertebral column is a pretty long object made up of all the little bony structures. So a particular person's vertebral column will be of a certain, an image will be generated from that. An image can be generated, a high-dimensional image, three-dimensional image, voxel space. It would have millions of voxels or three-dimensional pixels defining the vertebral column. And supposing we wanted to look up some other vertebral column that is similar to this one, or we want to speculate about what would happen if we make some small changes to it. Do we work in that very high dimensional space of millions of pixels, millions of voxels? Or is there some other lower dimensional representation? And we can say, well, this is just a point. This whole image of this particular vertebral column is a point on some manifold, lower dimensional manifold, need not be millions of dimensions, could be hundreds of dimensions. And then we are just moving along from one to the next. Let's say we want to compute similarity. Do we compute them in million dimensional space? The answer is no. If you know something about the manifold, you can look at it in manifold space and say, where is the next one? What would happen? What's the difference between these two? That kind of a thing. So you can see the practical value of moving from a very high dimensional raw representation that a scanner or an MRI or a CT scan would generate. And then we're saying, what is the kind of shape this is all about? So autoencoders in somehow are useful there for this. And also we want to learn the kind of manifolds that are present. So that's the topic. So we will begin by talking about what's called as the manifold hypothesis. First question we want to ask is, why does this happen? Nature says, well, you take an image and it's got a very high dimensionality of every point in that physical world. But we're saying nature also says that all of that space, all of that volume defined by the millions of pixels is not used. Most of it is empty. The particular object you are interested in is occupying only a small amount of space. And all the others of the same kind of object all occupy nearby points in this high dimensional space. So that's the nature of things. So we have raw input and then we have these low dimensional manifolds. So that is called as the manifold hypothesis. It's a hypothesis. Just nature is like that. And there's no proof for it. But objects tend to be like, they're not distributed all over. So we'll look at some motivations. Why is this true? And after we look at the manifold hypothesis, we get into a bit of specialized mathematics called topology. That sounds pretty scary. There is actually a mathematical definition of what is a manifold. The definition itself looks very strange. It involves words like homeomorphism. Wow, do we have to learn what is a homeomorphism? And what is a homeomorphism and how does it differ from homomorphism? So there are all these interesting concepts, homeomorphism, homomorphism, to define what do we mean by a manifold. We'll look at it. We are not going to get lost in all the math because the math can be pretty serious. We are getting into the topology. Topology means connectivity. What is next to what? Right? In topology, we talk about how objects have continuity, how the topology of a cube is different from a topology of a donut. You know, there's a ring with a hole in the middle. That's a different topology. Or we can have an object with two holes in it, right? Like a pretzel. There's a two-hole donut. So that's got a different topology. Or we can talk about topology is a shell. It's got a surface and there is a hollow in between. That's got a different topology. So we have objects which have different topologies, and then there is objects that have the same topology. So a solid cube and a solid sphere has the same topology. There's no hole in it. So we say they have the same topology, although the geometry is very different. So we talk about topology and geometry, and we define a manifold using algebra. Actually, topology. We define a manifold using topology, and then we define, and then there we bring in the idea of homeomorphism, which is also a concept from topology. On the other hand, homomorphism is a concept from algebra. So we'll just distinguish between the two, although homomorphism is not important here. So we'll talk about that a little bit. And after that, we get into how to define these manifolds and methods to regularize our learning process so that we still continue to define the manifold appropriately. So we get into some of these, and then we'll conclude with, once again, an example of an application which is in the area of three-dimensional structures of the human spine. And there's a paper on that topic. So that's what we're going to do. So that's the plan for today's lecture. So we shall begin with the slides, which I will try and bring up now. Okay, so I'm now sharing my slide deck for today's lecture. Hopefully it's visible to you. Otherwise you can just send me a message. So we have the topic of learning manifolds with autoencoders. So again, putting it into context, this is a pretty big chapter, chapter 14 of our deep learning book. And we're just covering it with 2 lectures. The first lecture covered what is an autoencoder, under complete autoencoders, regularized autoencoders, representational power, and we talked about variational autoencoders. So today we're doing number 6, which is learning manifolds with autoencoders. So that's the main topic for today. And the subtopics within learning manifolds with autoencoders, first is the manifold hypothesis. Why does data lie on a manifold? And then how do we define a mathematical manifold? And how do we specify manifolds in machine learning? Basically, we'll talk about the latent representation. The hidden unit representation defines a manifold. And then we get into how these manifolds can be specified by using tangent planes. So rather than specifying a manifold with all this continuity, which is a complicated looking surface, we could have a finite number of tangent planes which define the manifold. And then we'll talk about some specialized autoencoders. Okay, the first picture here is the standard picture of an autoencoder. On the left side, I think it's the night show host Jimmy Fallon, and we have an encoder that takes his image and creates the encoding in the middle here, and then that is subject to a decoder which recreates the image. Right. So the job of an autoencoder to take the input high dimensional. This is high dimensional because it's a high dimensional picture with a million pixels or so. The encoder takes it into a smaller number encoding. Shown here is a black and white, some vector of some sort. Shown here is a matrix. And then a decoder would use that and says, yeah, I can recreate it for you. Almost as good as it is. It loses information, definitely. But that's the objective of an encoder. While I was doing this slide on autoencoder, I was just reminded what do we mean by auto in India and in Bangalore? Is an auto, of course, is a 3-wheeler vehicle, and in a way, I was just thinking, isn't that something that when you travel in a auto, you get shaken up quite nicely, maybe converting us into a point on a manifold. And then, of course, when we reach the destination, hopefully we come out alive, almost like when we landed. So it's kind of an analogy here, but it probably illustrates a point. We have here a 3-dimensional object, which is X, this is a person, I suppose, maybe multi-dimensional object. And the encoder here, above we saw the box called encoder, is this auto rickshaw here, which is converting this object into a particular point H. It's not this entire manifold, it's a point H here. We refer to this as a latent representation. It can have many dimensions. It need not be flat. Whereas this is very high dimensional. This can be somewhat lower dimensional edge. And that point doesn't lie anywhere in this multidimensional space. It lies in a lower dimensional space as a sheet of paper here, or it could be a 100-dimensional or a 200-dimensional space. It's a point over there. And all the human beings who enter the auto rickshaw would all be points on this particular manifold. All right. So together, all the training samples define the entire manifold, and a particular individual is just a particular point on that manifold. And the decoder, of course, is trained. This encoder is trained with samples because the training takes place left to right. So we do back propagation to learn the method of representation H. So we learn both the encoding part and the decoding part. So the decoder would take that H as input and it would recreate, we call it as RFX, reconstructed X. RFX is not necessarily exactly equal to X, but some reconstruction of it. So an autoencoder, you can think of it as the auto rickshaw that converts you into a representation and recreates you from there. But keep in mind, it's not just you who creates the manifold, but every occupant of the auto rickshaw would create that manifold. All right. So that is the analogy of what an autoencoder and an auto rickshaw does. All right. I put this figure up last time. You see that particular manifold is labeled here as M. And this could just have been trained not on three-dimensional object, but images of a person, persons here. And maybe we make transformations of these little at a time corresponding to age, and they end up making movement along this manifold of a person aging here. Perhaps for the query, we can retrieve from that manifold what the aging person would be like. Similarly, for another individual, a third individual, and so on. So this, I got it out of a paper, which is about studying these manifolds from the point of view of observing how people age and traversing this manifold. So we'll take up this issue of manifold hypothesis. So the data concentrates around a low dimensional manifold. That's what is meant by a manifold hypothesis. And why are we studying this? What is the nature of this manifold? Is that some machine learning algorithms have unusual behavior if given an input that is off of the manifold. So we want to have some characterization of the manifold to make sure it is somewhere on the manifold itself, and we'll see how it's specified. And autoencoders aim to learn the structure of the manifold itself, which is kind of nice. Okay, here is another slide which tries to give you some more intuition of why does data lie on a manifold. So they take this fanciful example here. Suppose we want to classify all black and white images with m times n pixels. Each pixel has a numerical value. So we have an m by n, that is 1,000 by 1,000 pixels. And each pixel is a numerical value, maybe a shade of gray between, represented by 8 bits, 0 to 255. And an image is a single point of dimension n equal to mn. So if I give you a one photograph of Albert Einstein in this 1,000 by 1,000 grid, so it says, well, it specifies all the values for that 1,000 by 1,000. So given all the values for this 1,000 by 1,000, that is a million pixels, we have a point there represents the first picture of Albert Einstein. Supposing all images are photos of Einstein, supposing we have a large number of photos of Einstein here, and we are restricted on choice of values for the pixels. All right, so every one of them is a photograph of Albert Einstein. I suppose he was well photographed at that time of when he lived, all these famous photographs of Albert Einstein. So we can't say take random choices for all these m by n pixels. And would that give you another picture of Albert Einstein? Probably not. Albert Einstein had, I think, long hair, like many of us today, I suppose. In those days, he had a barber. Nowadays, we don't have barbers. But yeah, Albert Einstein's face would lie on some low-dimensional manifold. It won't be all over the m by n space. And random choices will not generate such images. So we expect there to be less freedom of choice. So the first point that we selected was the first photograph of Albert Einstein. The next photograph would be another point, probably not too far from the first point. Of course, there are very different looking photographs somewhere here, which might go a little further off, but they're all going to lie. This is Albert Einstein now becomes a manifold in this three-dimensional space. So any point we pick on that manifold or that sheet of paper is an Albert Einstein image, right? Any point off of it is not going to be an Albert Einstein image. So the manifold hypothesis states that this subset should actually live, this quote unquote live in an ambient space of lower dimension. We are referring to the total m by n dimension as ambient space. And this lies, Albert Einstein lies in a lower dimension. In fact, in a dimension much, much smaller than n. So very few of those points would really correspond to Albert Einstein. Of course, in this case, we have how many? We have 2, 5, there are only that many points. There are 10 images, I think, in this set. That would be just 10 points in this million dimensional space. You know, the number of assignments for a million dimensional space is absolutely enormous. Even if it is binary, it is 2 to the power of 1 million, right? The number of possible images with 1,000 by 1,000 is 2 to the power of 1 million, an impossible number. That's more than the number of molecules in the universe. So quickly we exponentiate. So anyway, we're going to be in a much lower dimension. So the manifold hypothesis says all of your training objects, whether it be vertebral columns obtained by MRI, or are there photographs of Albert Einstein, or are they photographs of people entering auto rickshaws, they are all going to be lying on a very low dimensional manifold compared to the space that is possible from the raw data. So we can now conclude that low dimensional structure arises due to constraints arising from physical laws. What constraints Albert Einstein to be only constrained to that much, or all human beings entering auto rickshaws? That physical law says a human being can only have these kinds of dimensions and cannot be like gas spreading all over, right? So these are all due to physical laws. They actually did a empirical study and a large number of 3 by 3 images. This is a large number of 3 by 3, that is images represented as points in R9. All right, it's a 9-dimensional space, just 3 by 3 pixels, right? The values they can take is anything. If you allow them to be just binary values, then it is 2 to the power of 9 is the size of the space. But if you allow grayscale like 256 values, it's going to be 256 to the 9. That can itself be big. So they looked at these 3 by 3 images, and they found, these were images, I guess natural images. They found that they lie on a 2D manifold known as the Klein bottle. You might have seen this thing. It's a Klein bottle. It doesn't have 2 surfaces. It's got only 1 surface. The outside and the inside merge together. It's called a Klein bottle. And so all these images will be points on this manifold, and they continually go round and round and round. And so it is interesting that the nature of this manifold comes in some real data. Here is some more examples of low dimensional manifolds embedded in high dimensional space. So we have human beings here on the left side. These are all people. I guess it might even be the same person with different camera views and different illuminations, right? So this person is rotating head more towards the light here, so on like that. They have a whole set. What they did here on the right-hand side is they formed a manifold by 3 phase sequences under different lighting conditions, rotating from profile to profile. What they did was they took all these photographs of this person rotating the face under different conditions and plotted into this high dimensional space. And then what they did was they projected it into a lower dimensional space defined by principal components analysis, which is a much lower dimensional space. And then they observed in a 3-dimensional space of principal components what these look like. Every one of them is going to be a point, but they have 3 curves in this, three curves in this 3-dimensional space, which is ambient lighting, right lighting, left lighting. So they use 3 types of lighting, and each curve here is a curve. It's a 1-dimensional object in 3-dimensional world here. So one was the right lighting, the other one was the ambient lighting, on the left lighting, and so on. So you see all of these fall in this kind of a lower dimensional space, and every one of them is a point. But as you keep changing it slightly with different lighting, they become a particular curve. So that is the nature of these manifolds here. It's a one-dimensional manifold. And you take a look here at phonemes in speech signals. When you have a speech signal coming to a microphone, that is usually analyzed by a sound spectrogram, which is based on, and then which is based on the discrete Fourier transform. And we create these DFT, discrete Fourier transform features. It's going to be high dimensional, representing the sound. And they again projected it into a low dimensional space, two-dimensional space created by principal components analysis. And then they had different sounds, oo, ah, e, these sounds. So over a bunch of people making the sound ah, those are all the blue points, and then the oo is all the red points, and then the e are all the green points. So they all lie on these manifolds in this low dimensional space. So any point here would correspond to an E for a different person or a different basic features. So that is, again, one is coming from image, the other one is coming from speech. And people have also studied, a recent paper I saw, we'll talk about it in one of our later lectures, is how speech has some underlying features we can think of on the timbre, tonality, what is being spoken, like ah, oo, e, and so on. These are all features that are entangled in what we observe. So what we observe in the speech spectrogram are all these entangled features. And one of the goals of deep learning is to disentangle the features. Tell me about this particular part of it and that particular part. Can you give me separately what is the timbre, what is the particular sound that's being uttered, and a couple more. I am sitting outdoors, so you can see some ambient noise coming through. It is an auto rickshaw on the street here, urging everybody to stay indoors and so on. So coronavirus is very much an issue here in India. Okay, so let's move on to the mathematics of manifolds. So let's look at a definition of a manifold, and let's not fear it. So a manifold is a topological space that locally resembles Euclidean space near each point. So here we have a manifold, a three-dimensional manifold on the left side, slightly discretized. And it's a surface. We don't want to think of it as a solid sphere. It's a surface. It's a 3D manifold in a space, an m-dimensional space. That is, in this case, it's a dimensionality of 3. And what it says is a manifold is a topological space that locally resembles Euclidean space. In Euclidean space, we usually, this is Euclidean space on the right here, R3 we call it. It's a grid. So you can move one step in each direction, X, Y, or Z. And we say that is what a Euclidean space is about. Locally, there is, you can move in any of these directions. You have a neighboring point. Similarly, we can think of a manifold as every point has a neighboring point in its own space, three-dimensional world. And so, of course, it's a surface. We're moving in a three-dimensional world still, right? But still living on the surface. So there is a connection between the surface and to the Euclidean space near each point. So we say an n-dimensional manifold is a topological space M for which every point X belonging to M has a neighborhood homeomorphic to Euclidean space Rn. So this is saying every point is homeomorphic to Euclidean space. What does that mean? Okay, let's then venture into topology and ask them, what do you guys mean by homeomorphism in topology? And they say homeomorphism is a continuous transformation, the one-to-one correspondence in two geometric figures or topological spaces that is continuous in both directions. So we are talking about two geometric figures or topological spaces. I mentioned earlier on, like this is a donut, which has got a hole. It's a particular topology here. And that could be homeomorphic to another object of the same topology. In this small diagram here, I've shown a cube and a sphere and a plate. They all have the same topology. And here we have an empty box here with a hole in it. And this is like one of those weights they use in a gym, right? It's got a round sphere with a handle on it. And then there is a ring here. They all have the same topology of a hole. And this is two boxes and a sphere with two rings. And this is a double ring here. They all have the same topology. So this says there is a one-to-one correspondence between two geometric figures or topological spaces that is continuous in both directions. So there's a one-to-one correspondence between points between one and the other. They correspond to the same topology. So homeomorphism is about relating neighboring points in objects with the same topology. While we are on this complicated topic of homeomorphism, you can also ask them, I've heard of homomorphism. Is that the same thing? And the answer is no, they're not the same thing. Homomorphism in algebra, you know, just to recall what a homomorphism is, the most important functions between two groups, it's about group theory, are those that preserve group operations, and they're called homomorphisms. And okay, what does that mean? A function f mapping G to H between two groups is a homomorphism when f of xy is equal to f of x times f of y for all x and y in G, right? So you're mapping points from G to H, and we say f is a homomorphism, is that f operating on a point x and a point y, if it's equal to f of xy, is equal to f of xy for all x and y in G, and that holds as well in the other group H here. So it preserves the kinds of operations between points. If you say we are multiplying these 2 points and that gives you a particular value, similarly, the same thing happens in the other domain. So it's kind of related, not exactly as homeomorphism, but it's homomorphism. This is in topology, this is in algebra. Okay, I just put that in as a recollection of what is this idea. So manifolds are involved things that involve the idea. So the takeaway message here is that a point on a manifold has neighboring points to it on the manifold, just like in standard Euclidean space, and while we are moving along that space. So the neighborhood is the important concept. So a manifold has a dimension. A 2D manifold is a surface. So here is a surface of a sphere. We saw that in the previous slide. Here is a sheet of paper slightly curved. That is a 2D manifold, it's a surface. And here is a surface of a donut, which is also a 2D manifold. In general, a 2D manifold, it could also be a union of several surfaces too. We can say, what if there are two sheets and so on? You know, the kind of analysis that we look at involve only one of them, but the same thing can be said of having multiple sheets also. A 1D manifold is a curve. Like this is a one-dimensional manifold. A simple circle I draw here is a one-dimensional manifold. And if I draw a loop like this, that's also one-dimensional manifold. What about this curve here? That is a one-dimensional manifold. I think we saw this figure last time. This is actually a one-dimensional manifold corresponding to a handwritten digit 9, which is being mapped from feature space. We took a 784 dimensional picture, 28 by 28 picture of a handwritten digit. And we simply took that image 9 and we kind of translated it, slowly lowered it from top to bottom and kept on taking new pictures. And so these became new points in this multidimensional space. And then we are mapping it into some two-dimensional space and then observing where that point lies. Well, it's going to lie on some looking line here. And this is 9 as we push it down and down and down and down and down and down. It's going up there. So this again is a one-dimensional manifold. So we have 2D manifolds, 1D manifolds, 0D manifolds. We can, in all of 3 space R3, we can think of it as a 3-dimensional manifold in a high dimensional space. So this is the complicated mathematics of manifolds. Here is a very interesting 2D manifold in R3, homeomorphic to R2. This is, the Earth, right? We got India over here. And starting at the North Pole, we draw a straight line here, almost down to somewhere in Indonesia. This is in maybe Jakarta. And we are drawing a perpendicular to that line here, heading towards Sri Lanka over here. So this angle is a 90-degree angle. And when we draw a line from here to the North Pole again, this is also going to be a 90-degree angle. This is 50 degrees. Isn't that interesting? You have 90 degrees here, 90 degrees here, 50 degrees here. All 3 of them total up to 230 degrees. This is not standard Euclidean distance. Whereas when you had a 2-dimensional surface here, if we draw a triangle here, this is 90-degree angle here, this is 40 degrees, this is 50 degrees. These 3 angles add up to 180, which is what we know about Euclidean algebra, Euclidean geometry, you should say. And so when you're on this surface, something else is happening here. That's because you're in a 3-dimensional world here, and this is a 2-dimensional world. I suppose atlases have to contend with this. You're mapping your 3-dimensional world onto a 2-dimensional atlas, which is a large sheet of paper on which you're representing that object. And so anyway, here we're showing, this is actually a 2-dimensional manifold in R3, in 3-dimensional space. And here we have just a 2-dimensional object in a 2-dimensional space. So this is the one that was the interesting one. So in mathematics, a manifold is a topological space that locally resembles a Euclidean space near each point. Just like there is for every point near the North Pole, we have other points here, or near Jakarta, we have Bali and all those places. They're all nearby places here. Although we are talking about a manifold here, the kind of closeness and all is similar to an ordinary atlas. We'd say, well, here are the nearby places to this particular place. That's what he's saying. A manifold, a topological space that locally resembles Euclidean space near each point. So a topological space may be defined as a set of points along with a set of neighborhoods for each point, satisfying a set of axioms relating points and neighborhoods, which is why the math gets a little involved. Okay, so that is our very high-level description of what we mean by a manifold. Let's come back to deep learning and talk about manifolds in machine learning. So we have in the observed m-dimensional input space, the data is distributed on an mh dimensional manifold. So we say the input data is in a high m-dimensional space. And then we have h is the latent space. So it's mh dimensional manifold. So we say x belongs to Rm. There's the point that belongs to this m-dimensional space. H belongs to RMH. Rm means all the points on the real space, m-dimensional space. This is the real values in a mh-dimensional space, such that x is Ggen is a particular function that's a mapping of h back to x here. So an autoencoder is doing this, is generating this same x back from a particular function here, where Ggen h is a smooth function. And we are showing that diagrammatically here. So let's take a look at this simple example. It's a really revealing situation here. Supposing we have a two-dimensional world, x1, x2, and we have a particular one-dimensional manifold here. It's going along here in this two-dimensional world. And so we say that this is a one-dimensional manifold in R2. This is a two-dimensional world. Any point here is a real point in two-dimensional space, out of which we have a manifold here. It's a nonlinear manifold. So we say the data is available in feature space X. So we're saying the data lies like this. Supposing it is something like a handwritten 9, you're just moving it along and you're getting different values of x1 and x2, and that's what we're getting. It's all the same object 9, and we're just observing it in different ways. So that's why it's creating. There's the manifold hypothesis coming into play. All those 9s are going to lie next to each other, creating a particular transformation. H is not measured, but that particular H could be a latent representation. So we have this x1 coming in here, x2 coming in here, and we have an H, a representation here. And that is the plot of x1, x2, and H here. And there is an above graph here, which is that's the interesting part, that these correspond to x1 and x2, the feature map of H natural and into x1 and x2. This is the mapping for x1 and x2 created by the recreated version of it here. So why are these things looking like Gaussians here? You can see that originally x1 was allowed to go from here to here, and then x1 is only becoming smaller. If you just look at x1, it keeps increasing here and then keeps decreasing here, and then all the way decreasing here, all right? So in a way, x1 corresponds to something that is increasing first and then decreasing. Whereas x2, if you observe x2 in this graph, it is, if you go from here, from the bottom, it's increasing, and continually increasing up to this point, x2 is increasing. And then x2 is decreasing. So it says continually we are increasing here, and then we are decreasing. So that's the x2 is the feature map. So we are observing only x1 and x2, but the data is falling along a manifold, and we are able to recreate the object back into x1 and x2 values. See, we go from x1 and x2 to the autoencoder back to recreating x1 and x2. And while we are observing the data from the manifold, H has been created over here. And from the H, we are regenerating the values that look like these functions. The decoder is doing something very clever over here. This is an extremely simple example of the idea of a manifold and an autoencoder, which kind of tries to bring this idea alive. So now we move on to say that these complicated manifolds can be specified by tangent planes. So a tangent specifies how one x can change while staying on the manifold. So we look at two cases. One-dimensional manifold, this is a space of y as a function of x. All right. So now y is this function over here, and then we are drawing a tangent at a particular point here. So we say y equal to f of x is this function. All right. Y is this function, and at a point x equal to x naught, we can say, we are bringing in some famous calculus theorem, which is called Maclaurin's, or is it Taylor series? I think it's a Taylor series. It's a Taylor series expansion, or maybe Maclaurin would be at Taylor series at 0, I believe. So this is Taylor series. So it says y is equal to at a particular point f of x naught plus f prime, that's the derivative x minus x naught. So given the value of the function at some point, I can tell you the value of the function at some other point x. All right, given, so we know value of x naught, so f of x naught, that value we know. So we need the derivative at that point, at that x naught. And then x minus x naught, distance of x to x naught, that is approximately equal to y. It involves only the first derivative. Taylor series says you need to include second derivative, third derivative, and so on. But most of it is captured by the first derivative. That's the tangent. This is a two-dimensional case where z or z equal to f of x, y. There are 2 points here, x and y. Z is the third dimension. And similarly, just like one-dimensional case, at point x naught, y naught is given by z equal to f of x naught, y naught. Plus, now we have two types of derivatives, partial derivatives. Derivative along x and derivative along y. So it's fx of x naught, y naught, x minus x naught, and then fy of x naught, y naught, y minus y naught. So we can say that a point, the value of the function at any point can be obtained by the value given at another point, approximately. They should also set approximately here, because we're using only first derivatives. So at a point x on a d-dimensional manifold, the tangent plane is given by the d basis vector that span the local directions of variations allowed by the on the manifold. So this is saying in the local area of a given point, the derivatives are able to specify for you what is the value of the function. So if I know the value at this point, I can know the values at nearby points by knowing the tangent at that particular point. And if you recall, the derivative is nothing but you draw a tangent here and you take the ratio of the vertical value to the horizontal value is the value of the derivative. That is the same as the tangent. So you're saying manifolds are specified by tangent planes. That's because they are being specified by Taylor series. It involves the derivatives, and derivatives are the same as tangents. Isn't that beautiful? So we have a nice connection here between tangents and manifolds. So this is expanding on the same thing. This is looking at the same one-dimensional manifold for nines we have, and at a particular point, they're drawing a tangent to this. And the tangent is the derivative of that point in this multidimensional space. So when you take the derivative, it becomes a derivative of the image itself. So that's what they're showing over here. This is again one-dimensional manifold and 784 dimensional MNIST. This is the famous handwritten digit data set with 784 pixels. And the manifold is obtained by translating the image vertically. And the figure below is a projection onto 2D space using principal components analysis. And the n-dimensional manifold has an n-dimensional plane. In this case, it's one-dimensional manifold. It's got a straight line here. And the tangent is oriented parallel to the surface at that point. And the image shows how this tangent direction appears in image space. Gray pixels indicate pixels that do not change as we move along the tangent. And white pixels indicate pixels that brighten and black that darken. So you can talk about a tangent image to it. So this is a tangent plane in 3 dimensions now. This is a two-dimensional surface, which is this surface over here in a 3-dimensional world. And at a particular point, we're drawing a tangent plane, because what can happen is at a given point, you can have many tangent straight lines. All those tangents lie on this plane, so we're talking about tangent plane. So basically, these manifolds, whether they are on a line or whether they're on a surface, can be specified by tangents, which may be straight lines or which may be planes. Okay, so we're saying, okay, you can use tangents. So let's move on. So an autoencoder performs a trade-off between two forces. This we saw already. This is pretty basic about autoencoder. It learns representation H of a training example such that X can be recovered through a decoder. X is drawn from a training data is crucial. It means the autoencoder need not reconstruct improbable inputs. So we're only training it on handwritten digits, or if it is auto rickshaw is our encoder, only people are entering. We don't have any other objects getting into it, because it's going to learn what happens to people. Right? If you take in animals, I suppose that would have to be another plane or something. So anyway, handwritten digits of a certain class, maybe 7 or 8 or 9. And so it learns a representation H. So what is the representation for this class of objects? And at the same time, it has got another thing to do. It has got to satisfy what we call as a regularization penalty, which we say limits the capacity of the autoencoder. It cannot be arbitrarily complicated manifold it's going to create, which will be exactly like the idea of overfitting in supervised learning. Remember, this whole autoencoder business is all unsupervised learning. We are just learning how to represent data. There's no such thing as this is a particular person A, person B, person C. It's just a whole population we have, and we are learning the distribution of this population. And so in unsupervised learning, we can limit the overfitting, which we call it as limiting the capacity, by a regularization term that is added to the reconstruction cost. So we are using a loss function between x and g of f of x. F is the mapping function, encoding function. G is the decoding function. So g of f of x. How badly distorted was x? Like, you know, this is the auto rickshaw experience. This was the person who entered the auto rickshaw. And we are comparing what shape is this person in after the auto rickshaw ride. That is the loss. That loss should be as small as possible, right? And then to that, we are adding an omega of h, which is saying that h cannot be extremely complicated. So it's got to be, you know, we're converting it into a manifold, which is like a sheet of paper or something. Don't make it too crumpled a sheet of paper like that. That's some kind of a regularization. Together, they force the hidden representation to capture information about the data generating distribution. So a simple example here about capturing a manifold structure by invariance. So this is talking about, you know, you want to capture the manifold structure. So when reconstruction is insensitive to perturbations around the data points, autoencoder recovers manifold structure. We don't want it to be highly sensitive to changes on the data points. And this is a one-dimensional case here. We are plotting x is the input, r of x is the reconstructed, right? So the ideal would be this dotted line along the 45-degree line here, which says for x, we should have a reconstruction r of x exactly equal to that, right? So that's what we expect it to be. So this is called the identity. And we have some algorithm here that does its best, because you're only giving it 3 people, x0, x1, and x2 as the data inputs. You're not giving a whole population of Bangalore as input to the auto rickshaw. We only have 3 people entering the auto rickshaw. So that's x0, x1, and x2. At the end of the ride, you got to have a reconstruction of x0, reconstruction of x1. It's exactly the same. You see, in this point, the reconstruction is correct. Reconstruction is correct because it's coinciding with that point. But otherwise, it is trying to go along and find whatever it is, that because it doesn't know anything more about it. So this is the optimal reconstruction. It got the points right. So dash diagonal is the identity function for the target of reconstruction. Optimal reconstruction function crosses the identity function wherever there's a data point. And the horizontal arrows at the bottom indicate Rx minus X reconstruction vector, that's the difference between the two, direction vector, always pointing to the nearest manifold, a single data point. So this is saying we should be getting close to the data points and not reconstruct too far away. So that kind of constrains this construction function to not go away too far. So that is the mathematical way of specifying it. So then we'll ask a few more general questions as we're coming to the end of this learning manifolds. Why autoencoders are useful to learn a manifold? And there are other approaches too. Autoencoders characterize a manifold, represents data on or near the manifold, and representation of a particular example is an embedding. That's a strong message that's coming through here. You've done a course on deep learning and you're saying, what does deep learning do for you? Mainly, it creates an embedding from the real world into this latent world, which is capturing the essence of your data. So the manifold is that capturing of the essence. An embedding has fewer dimensions, and the ambient space of which the manifold is a low dimensional subset. But there have been other algorithms for capturing manifolds. One are called non-parametric manifold algorithms, which directly learn an embedding for each training example. So you can say, well, I will just learn an embedding for each of the 3 passengers you got. Okay, I'm going to learn an embedding for each of these separately. I'm not going to worry about what is in between the 3 passengers. So we are not learning the manifold, but we just learn these 3 and do some kind of a fit between the 3, interpolate or extrapolate between them. So we can say, well, we got the embedding for one, we got the embedding for another one. This one has to be somewhere in between. That is referred to as the nearest neighbor method. Or there are other algorithms learn a more general mapping, a function to map points in ambient space to embedding. So there are a few other methods which we'll look at. So this is that first thing I mentioned, non-parametric manifold learning, which is to build a nearest neighbor graph where nodes represent training examples. So we're building a mathematical graph where nodes corresponding to each training example. Look at this data set here. The particular data set called the Queen Mary, I think QMUL it's called, Queen Mary University of London multi-view face data set. So they got all this, the same person's face it looks like, rotated all around from, and the person's face is being moved from top to bottom and so on. So they had a data set like that. And so they build a graph from it. And nodes represent training examples, 1 node per sample, and directed edges indicate nearest neighbor relationship. That is, this is right next to the other one, like that. So procedures to obtain tangent plane associated with a neighborhood of the graph. So you can think of each of these faces being a point on a manifold and associate each training example with an embedding vector. So we run them through the autoencoder, some autoencoder where we didn't pay much attention to the manifold issues. And so they all become points on some manifold. We just know the embeddings. And if you have a number of examples is large to cover manifold twists, you see this manifold can have amazing twists. When the face suddenly turns around, you can't see one eye. I imagine that the embedding vector is going to look quite different. So the manifold is going to take a nice turn there. Maybe that's why we end up with Klein bottles and things like that in this embedded space. So the method associates each space with a tangent plane. Okay, we have a space and we associate a tangent plane, just like we talked about. One that spans the directions of variations associated with difference vectors between example and its neighbors. How do you get a tangent? You look at the point and its neighboring points. You can define the derivative, which corresponds to the tangent directions in each of the directions, X, Y, and Z. And that way you got the tangents at each point. And we can now tile a manifold saying, okay, forget about all those faces. Let's just look at the manifold you got. That manifold corresponds to all the faces. And we have a global coordinate system can then be obtained through optimization or by solving a linear system. All right, we apply some math. A manifold can be tiled by a large number of locally linear Gaussian-like patches or pancakes. The Gaussians are flat in the tangent directions. So we can think of flat Gaussians at each of these points. And so we have tiled this manifold, which is really a mixture of Gaussians. And we are saying, okay, so that is the nature of this manifold. So what can you do with it? You got all these Gaussians, you got this manifold. If you wanted to generate a sample, you can generate it. If you have a sample and says, where does it lie? It lies over here on this manifold. And how far is the other one to this? You can go along the manifold rather than some other way of measuring the similarity. So these methods can only generalize the shape of the manifold by interpolating between neighboring examples. Unfortunately, manifolds in AI problems are very complicated that can be difficult to capture from only local interpolation. So this is slightly older method, which is simply obtain the embeddings and tile a manifold, and can't you use it? It's saying real world AI problems are much, much more complicated, and that simpler method may not work well. And what's an example of a real world problem? Here is one that I came across. This is a paper, I think, of this year on medical imaging. So I don't understand all the medical imaging terminology here, but it's kind of something you can get a sense for. Here is the vertebral column. Apparently, this vertebral column consists of these little subparts. I don't know what they call it, but all these little pieces together, they constitute the vertebral column. There are so many of them, I suppose, that constitute the vertebral column, and they labeled it as S1 through SL, right? And this is this is a particular case. In this particular square region, this is as the jth piece of the vertebral column here, and this is the jth piece. This is the j minus 1th piece, and this is the j plus 1th piece, right? This is j plus 1. This is j minus 1. And each of these has a different direction. Seems to be pointing here, this pointing like that, this pointing like this, and so on, which I guess there is a change in direction going on in this particular part, which is why it's going like that. And so what they're showing here is, what is interesting is, they refer to this as articulation of the spinal cord. And this particular spinal cord is this little plus over here on this manifold M in some d-dimensional space. So the original space could have been an MRI or CT or ultrasound, which is very high dimensional. That has been mapped by an autoencoder into a lower dimensional space. And this particular one is being mapped over here. That's this plus. And we could think of small variations of this, I suppose, of each of these different parts as moving along, as we change the orientations, as moving along this particular manifold. So they're saying that this manifold is induced by articulated based metric. Maybe they're using some metric measures of distance, and learned data manifold. So there's a learned data manifold. And in this paper, they began by saying, we're going to try a different method than what has been used so far for spinal cord analysis. They're saying linear techniques are unsuitable for capturing variations in anatomical structures. What they're complaining about is, if you had simply a structure saying, here is a spinal cord in your MRI data, high dimensional space, and I want to make some movements of this, I can't simply go by changing some pixels here. That gives you nonsensical results. Or if I want to compare it against the same patient's spinal cord taken maybe 10 years ago, how would you measure the similarities of the two? You can't simply go by pixel again. You'll get again very arbitrary results. So this is saying you must capture the nature of this one, and nature is captured by the manifold. And then now on this space, you can now talk intelligently about different spinal cords or what could happen, things like that. So you see the power of this manifold learning in medical imaging. I was searching hard to see other examples. I couldn't find too many yet. This seems to be a nice example of the use of manifolds in particularly medical imaging. So we're almost at the end here. The remaining slides are some variations of autoencoders. Overcomplete autoencoder is when the dimensionality of H is higher than the image input, then you're going to get, this is called overcomplete, which is not going to be very useful. Contractive, of course, is a method to avoid uninteresting solutions, add explicit term in the loss that penalizes that solution. And we wish to extract features that only reflect variations observed in the training set. We would like to be invariant to other variations. So this has all got to do with the loss functions that are used to do the backpropagation. You're going from input to output through the encoder and decoder. What kind of loss function should you use when you compute derivatives to do the backprop? And that is kind of shown over here. For example, in a contractive autoencoder loss function, we have that omega of h. We saw that we're going to use a loss function, and in this case, explicitly saying that that loss function has this form lambda times this is the squared Euclidean norm of the derivative of f of x. F of x is a particular manifold h, right? So we are encouraging the derivatives of f to be as small as possible. So a contractive encoder is a particular one that is saying this loss function as an omega that is not the standard ones we know of from basic deep learning, where we talk about the squared loss, all right, or the we have so many names for that there, right? So that's the very basic ones we talk about. So this particular one is referred to as the squared Frobenius norm, sum of squared elements of the Jacobian matrix of the partial derivatives. So you see, we can relate it to the partial derivative matrix, where we're taking the derivatives in all the directions in your space. And if you remember, Jacobian is all about derivatives. So we have a Jacobian matrix, and that is what comes into play into the, so for example, the equation now, the loss function is the autoencoder, first term. It's a standard loss here. And a lambda times Jacobian of the encoder function is coming into play here. And that is a particular name called Frobenius norm. And this kind of expands out what all the terms are. It's just really fascinating to see how to train these autoencoders properly. There's also idea of denoising autoencoder. I skipped that part. That was an earlier section of before today's lecture. But there's so much to cover that I decided, okay, let's skip DAE, the denoising autoencoder, which is yet another nice variant. And these contrastive autoencoder warps the space by using the derivatives, right? So this is the last of chapter 14, which is about autoencoders. The first part was simply defining autoencoders. The second part was all about manifolds. And we are not done with this topic. The next chapter, chapter 15, is all about learning representations. Well, what more is there to know about representations? We talked about manifolds, but there we talk about this interesting idea of disentanglement. And that is the key concept, that the world is entangled. I mean, this is a concept of human living, right? We say that our lives are all entangled with so many factors, and saying, can you disentangle it, separate them out? Maybe you can solve each of these, and if you know what the entanglements are. Which the same thing happens here. That to understand any kind of data that you're getting, for example, even that, the idea of speech. When you are getting into the microphone, the speech, it is an entanglement of the words that are being spoken, the rhythm of the speech, how fast it is spoken, how slow it is spoken, how the pitch of it, whether the speaker is nervous or not so nervous, that also affects the speech. So there is male or female. So we got, so the final product we are seeing is it's a male voice, a certain low pitch or a high pitch, and what the speaker is speaking, what is the emotional state of the speaker, nervous or not so nervous, or melodious, and so on. So the final product is an entanglement of all of these separate factors. So is it possible for a deep learning mechanism to disentangle all of these and present to you clearly what that speech signals components are, so that you can learn a lot by looking at these separate components? So that again becomes a kind of representation. Not that there are extremely good solutions. Papers are just coming out. I just saw one today on this speech disentanglement. using deep learning. So I thought we'd touch upon it when we get into chapter 15. Okay, I'm going to stop there, and happy to take on any questions you might have. Okay, so as I mentioned, slides for today and are available already, and the video also is available on YouTube as well as on Facebook. And you can also find it on my homepage link. If you Google me and go to my homepage, I have deep learning slides there, and I'm trying to link up these videos so students who are not in this class can also take advantage of that. All right, so take a look at chapter 15. We're beginning a new chapter. We're covering these chapters a bit faster than earlier on. Chapter 15 will take us definitely 2 lectures, hopefully not 3. And then we go on to generative models after that, okay? All right, have a nice day and see you back on Wednesday.